There is a particular kind of quiet that belongs only to an astronomical lens workshop before sunrise. It is not the silence of an empty space, it is the dense, suspended quiet of materials cooling at microscopic increments, waiting for human hands to resume measuring what the eye cannot see on its own. My name is Alan. I work as an optical surface technician in a specialized precision laboratory situated on the rural edge of the northern province. For 8 years, my work has been defined by tolerances smaller than the wavelength of visible light. When you spend 10 hours a day holding a diamond grid lamp against a disc of borosilicate glass, checking the curvature against an optical flat under sodium vapor light, you learn that surfaces never lie. Glass remembers every particle of grit, every fraction of a degree in temperature change, and every second of uneven pressure. My life outside the workshop is deliberately quiet. I live alone in a small stone cottage 3 miles down the valley road. I walk to work at 6 in the morning, make a pot of strong black tea on the laboratory hot plate, and begin by checking the thermal stabilization logs for the curing ovens. I do not like surprises. In my profession, an unexpected variation in curvature is not a discovery, it is a ruined blank that costs 4 months of grinding and polishing to replace. The laboratory itself is a single-story granite building constructed 40 years ago over a thick basalt bedrock pad to eliminate ground vibration. We fabricate custom refractive lenses and parabolic mirrors for regional observatories, meteorological stations, and high-altitude atmospheric research units. Because of the extreme precision required, our work area is divided into 3 temperature-controlled chambers: the rough shaping room, the fine polishing bay, and the central optical testing tunnel. On a cool Tuesday in late September, I was preparing the testing tunnel to evaluate a 60-centimeter refractor lens that had spent 3 weeks undergoing final hand figuring. The lens had been ordered by a high-altitude meteorological station perched on the mountain ridge 40 miles to the west. Their instruments measured solar radiation and upper atmosphere thermal inversion layers, tasks requiring an optical glass blank free of internal stress fractures or refractive anomalies. The evaluation process relies on the Foucault knife edge test, a century-old optical method that converts microscopic surface imperfections into dramatic patterns of light and shadow. You place a pinpoint light source at the center of curvature of the lens, align the returning beam with a razor blade, and cut the light path precisely at the focal point. If the glass surface is a true, perfect sphere, the lens darkens completely and evenly all at once, fading into a uniform, velvety gray. If there is a raised ridge or a low zone even 1/100,000th of a millimeter off, the flaw casts a sharp shadow across the disc like a mountain ridge caught in low sunlight. I locked the heavy soundproof door of the testing tunnel, checked the thermometer mounted on the central pillar, precisely 66 degrees Fahrenheit, and turned on the monochromatic green LED light source at the far end of the 30-foot track. I sat on the low iron stool, adjusted the micrometer thumb screws on the knife-edge carriage, and looked through the viewing port. I slid the razor blade slowly across the returning cone of light. The glass disc began to darken from right to left as the blade intercepted the rays. As the focal point aligned, the glass transitioned into that deep, flat optical gray that tells a technician his polishing strokes have been true. Then the shadow hesitated. Near the upper left perimeter of the lens, roughly 3 inches inside the polished bevel edge, a thin, curved line of light remained sharp against the gray background. I did not move. I did not take my hand off the fine pitch adjustment screw. In precision optics, your first assumption when seeing an irregular fringe is always an external artifact: a stray hair from your sleeve resting on the surface, a microscopic smudge of dried alcohol from the final lens wipe, or a rising thermal plume caused by your own body heat warming the air between the stand and the tester. I stepped away from the viewing port, waited 2 full minutes for the air inside the closed tunnel to stabilize, and turned on the overhead inspection lamps. I pulled on a clean pair of lint-free white cotton gloves, picked up an aerosol canister of filtered optical-grade dry air, and blew across the upper quadrant of the lens. Then I took a long-wave ultraviolet inspection lamp from the wall bracket and swept the beam across the face of the glass. The surface was pristine. There was no dust, no dried solvent film, no scratch in the optical polish, and no coating defect. The glass was immaculate, polished to a mirror shine that reflected the white laboratory ceiling like still water. I switched off the overhead lamps, plunged the tunnel back into absolute darkness, and returned to the Foucault apparatus. I engaged the green light source and slid the knife edge across the beam once more. The uniform gray shadow swept across the glass. And there, in the exact same spatial coordinate in the upper left quadrant, the thin line of light reappeared. Except it was not an irregular curved fringe. Under the razor-sharp focal cutoff, the light and shadow formed distinct, geometric lines. They were thin, crisp, and deliberately shaped. I leaned closer to the viewing port, turning the micrometer screw by a fraction of a millimeter to sharpen the contrast. Inside the interior volume of the solid glass blank, suspended exactly midway between the front convex surface and the rear concave face, was a 4-digit sequence. 8 to 4, 1 to 2. The numbers were not etched onto the exterior. They cast a shadow because the glass inside those 4 glyphs had a fractionally different refractive index than the surrounding borosilicate matrix. Someone had shaped, annealed, and sealed those digits into the molecular core of the blank before it was ever delivered to our grinding table. I stood up straight in the dark tunnel, my fingers resting on the cold steel frame of the carriage. The lens blank had been shipped to our facility inside a heavy wooden crate sealed with industrial strapping, accompanied by a standard metallurgical certificate from the regional casting foundry 30 miles south. The certificate stated that the blank had been cast from a single, uniform batch of molten optical crown glass, melted in a ceramic crucible, and cooled in an automated lair over 45 continuous days. A casting furnace does not accidentally form 4 legible, upright Arabic numerals inside the center of an optical blank. I turned on the tunnel lights, opened the door, and walked across the workshop to find Marcus, our senior workshop manager. Marcus was 62 years old, had spent 40 years grinding mirrors for university observatories, and believed that every optical anomaly could be solved with 5 more hours of cerium oxide polishing. Marcus was at his workbench, drinking tea from a chipped ceramic mug while reviewing the week's abrasive delivery slips. "Marcus," I said, keeping my voice level. "Come into the testing tunnel. I need you to look at the meteorological blank." Marcus looked up over his half-moon reading glasses, setting his mug down with a small clatter. "Did you leave a low zone on the edge, Alan? I told you that 5-inch lap was pressing too hard on the outer radius." "The figure is flat, Marcus," I replied. "Just look through the port." Marcus followed me into the tunnel, muttering under his breath about changing humidity. He sat on the iron stool, bent his back, and aligned his right eye with the knife-edge port. I turned off the overhead lights and engaged the green test beam. Marcus adjusted the micrometer screw back and forth twice. He went completely still. For 20 seconds, the only sound in the tunnel was the low, steady hum of the air circulation intake. "That's internal," Marcus said softly, his voice losing every trace of its usual gruff impatience. "That's not surface figuring. That's a localized refractive density shift inside the melt." "Read the numbers," I said. Marcus paused, his eye glued to the aperture. 8, 4, 1, 2. They're about half an inch tall. The edges are crisp. It looks like molded glass inserts with a slightly lower lead content fused into the core during the initial ladle pour. The casting manifest from the foundry says this blank was poured as a single monolithic block on August 3rd, I said, pointing toward the clipboard hanging by the door. "Batch number 76. Signed off by their chief metallurgist." Marcus stood up slowly, rubbing his eyes with the back of his hand. He turned on the room lights and walked over to the wooden lens stand, staring at the 60-centimeter glass disc resting securely in its padded cradle. Under the bright fluorescent tubes, the glass appeared entirely clear, transparent, and flawless. You could hold a printed newspaper behind it and read every word without the slightest distortion. "It's a foundry identifier," Marcus suggested, though his voice lacked conviction. "Some casting houses embed glass marker tags into large industrial blanks to identify production lines in case the external paper tags get torn off during transport. Foundry identifier tags are placed on the outer edge, outside the clear optical aperture," I pointed out immediately. "They use ceramic ink or laser stippling on the unpolished rim. You don't embed a refractive density variation 3 inches inside the usable field of a precision meteorological refractor. Any light passing through those 4 numbers will suffer a localized phase shift. It renders the lens useless for high-precision focal imaging." Marcus crossed his arms, staring down at the floor tracks. "If the blank is defective, we reject it. We file a non-conformance report with the regional supply board, send the glass back to the foundry on the Friday truck, and demand a replacement casting. And what do we write on the rejection form, Marcus? I asked. That the foundry poured a 4-digit security code into the middle of a piece of optical glass. Marcus did not answer right away. He reached into his apron, pulled out a clean magnifying loupe, and walked around the lens stand, examining the polished bevel from every possible angle under direct white light. The numbers remained totally invisible. They require the extreme sensitivity of the Foucault test, a setup that split light at its exact optical focus, to manifest. We don't send it back until we understand how it got there, I said quietly. Because if this was done at the foundry during the pour on August 3rd, it wasn't a metallurgical accident. It was manufactured with intent. I walked back to my desk, opened the heavy linen-bound workshop ledger, and pulled up the original procurement file for the Mountain Weather Station's refractor project. The order had not come through our usual university channels. It had been submitted 3 months ago through the Regional Public Infrastructure Department, signed by a technical director named Victor. Attached to the purchase requisition was a single specific instruction written in red ink on the margin of the technical specifications. All optical blanks must be sourced exclusively from the Southern Valley Casting Facility, Unit 4. I looked at the 4 numbers I had written in my notebook, 8 to 4, 1 to 2. Why would an infrastructure project specify a single casting unit for an ordinary atmospheric lens, and what was the sequence inside the glass designed to measure? A precision instrument maker does not begin an investigation by looking for conspiracies, he begins by checking his calibration gauges. When an unexplained mark appears inside an industrial material, the first professional obligation is to eliminate every mechanical, chemical, and procedural step that could have produced the anomaly through routine operation. On Wednesday morning, I arrived at the workshop an hour before sunrise. My goal was simple and systematic. I needed to verify whether the embedded numbers 8 to 4, 1 to 2 were unique to the 60-centimeter meteorological lens, or if they were the result of a standardized manufacturing tool used across the Southern Valley Casting Facility. I began by pulling our historical inspection records for the past 3 years. Our workshop was small, but we maintained rigorous physical documentation for every glass blank that crossed our threshold. Each delivery was logged in a heavy gray binder with its batch number, dimensions, annealing cooling curve, and the initials of the technician who performed the incoming optical inspection. I spread the inspection logs across the large sink-topped assembly table in the rough shaping room. Over the past 36 months, our facility had received 24 large aperture blanks from the Southern Valley Foundry. 14 had been fashioned into mirrors for astronomical telescopes, 6 had been ground into flat optical windows for high-pressure research chambers, and 4 had been shaped into refractive lenses for regional survey equipment. Of those 24 blanks, 20 had been ground and polished without any noted internal density shifts. But when I reached the entries for the survey lenses processed 9 months earlier, I found a brief note written in Marcus's tight, slanted cursive. Blank SV409. Minor internal wave detected in quadrant 3 during rough figure. Attributed to cooling eddy in the layer. Pass for low magnification survey use. I read the entry 3 times. A cooling eddy is the standard workshop explanation for any minor refractive variance that does not affect the final focal performance of a low-grade instrument. It is the kind of phrase an experienced technician writes when he wants to finish his shift and move an acceptable piece of glass to the shipping rack. I walked to the storage bay at the back of the building. On the lower shelves of the secondary inventory rack sat 4 completed survey instruments that had been returned by the Regional Civil Engineering Office 2 weeks prior for routine seasonal cleaning and realignment of their brass mounting rings. I selected the first survey refractor, a 10-inch brass barrel telescope fitted with an achromatic doublet lens. I carried it into the testing tunnel, unbolted the front retaining ring with a non-magnetic brass spanner, and carefully mounted the objective lens into the Foucault testing cradle. I turned on the green light source, extinguished the room lamps, and aligned the knife-edge carriage. I slid the blade across the focus. The glass disc darkened. At first, the field appeared completely smooth, resolving into the clean, uniform gray of a well-corrected optical curve. Then, as the knife edge cut the final rays at the focal center, a faint, razor-thin line of shadow emerged in the lower right quadrant. I adjusted the micrometer screw by 5 microns. The internal density shift resolved with unmistakable geometric clarity. Suspended in the molecular center of the 10-inch survey lens was a 3-digit sequence. 8-4-1. There was no fourth digit. The numbers were half the size of those in the meteorological lens, but the font, proportions, and depth of placement were identical. They sat inside the glass matrix like a watermark pressed into wood paper during manufacturing. I sat back on the iron stool, my pulse steady, taking down the exact coordinates in my notebook. 2 lenses. 2 separate casting dates 9 months apart. Both sourced from the Southern Valley facility. Both exhibiting internal refractive variations that formed legible numbers under knife-edge testing, while remaining entirely invisible under standard ambient lighting. At 8 o'clock, the laboratory telephone rang. It was David, the chief logistics coordinator for the Regional Infrastructure Department, the administrative office that managed procurement for both the survey teams and the Mountain Meteorological Station. David was a bureaucratic functionary who viewed our workshop not as a center of fine craftsmanship, but as an entry on a quarterly equipment ledger. "Alan," David said, his voice coming through the receiver with the tinny, hurried tone of someone speaking from a noisy municipal office. "The transport team is scheduled to pick up the meteorological refractor tomorrow morning at 9. The mountain station has their installation crew on site to mount the objective before the autumn snowstorms close the high pass." "The lens is not ready for release, David," I replied calmly. There was a brief pause on the line, followed by the sound of shuffling paper. "What do you mean it isn't ready?" "Marcus sent the preliminary schedule 3 weeks ago stating the final figuring would be completed by Tuesday." "The surface figuring is complete," I explained, choosing my words with precise professional neutrality. "The curvature is accurate to 1/20th of a wave. However, during final optical testing, I detected a significant internal structural variance within the glass matrix. The blank does not meet the specified refractive homogeneity standards for high-altitude solar monitoring." "Is the glass cracked?" David asked. "No. It is structurally sound, but optically non-homogeneous." "Alan, this is a regional weather installation, not a deep space astronomical research observatory," David said, a note of exasperation creeping into his voice. "They are tracking thermal inversions and cloud density across the valley. If the lens is structurally intact and holds its focus, minor glass imperfections are within the acceptable tolerance framework established by the Regional Oversight Board." "This is not a minor imperfection, David," I said firmly. "It is an intentional, organized inclusion within the core of the blank." The line went completely silent for several seconds. "What kind of inclusion?" David asked, his tone shifting from bureaucratic irritation to guarded caution. "I need to speak directly with the casting supervisor at the Southern Valley Foundry," I said, avoiding a direct explanation over an unverified line. "I need the cooling logs and crucible assignment sheets for batch 76 before I can sign the release certificate for this assembly." "The casting supervisor is a gentleman named Thomas," David replied after a moment of hesitation. "He oversees industrial furnace operations. But I can tell you right now, Alan, the casting facility operates under strict technical directives. If you refuse to sign that release certificate, you will delay a municipal project that has already exceeded its annual capital allocation. An instrument that leaves this workshop carries my signature on the optical certificate," I said evenly. "I do not certify materials whose internal composition contradicts the casting manifest." I hung up the telephone, took off my shop apron, and walked into Marcus's small office. Marcus was sitting at his drafting table, examining the mechanical drawings for the weather station's steel mounting barrel. "David called," Marcus said without looking up. "He thinks you're being overly meticulous." "I tested the return survey refractor from the storage bay," I told him, placing my notebook on the edge of the drawing board. "Blank SV409 has the sequence 8-4-1 embedded in the lower quadrant." Marcus stopped his pencil. He looked at the notebook, then up at me, his weathered brow furrowing deeply. "That's 3 numbers. The new lens has 4. Which means it isn't a random serial stamp," I said. "It's an expanding sequence. A positional code." I walked over to the large regional map pinned to the workshop wall. The northern district was dominated by 3 geographical features: the wide agricultural valley in the center, the industrial river district to the south where the glass casting foundry and heavy manufacturing plants were located, and the sharp granite mountain ridge to the west where the meteorological station stood overlooking the entire territory. I took a pair of drafting dividers and measured the line of sight between the mountain summit, our workshop in the valley, and the southern industrial sector. The mountain meteorological station sat at an elevation of 6,000 feet, providing an unobstructed panoramic view across 60 miles of the valley floor. If an optical instrument with a focal length of 8 feet were mounted in that tower, aimed through an objective lens with a deliberate internal refractive deviation, what would the observer actually see? To an observer looking through the eyepiece with the naked eye, the view of the valley would appear entirely normal. But if the light collected by that lens were split through an optical filter or analyzed by an interferometer, the standard instrumentation used in atmospheric monitoring, the embedded numbers inside the glass would act as a permanent optical reticle, projecting a precise mathematical grid over specific coordinates of the landscape below. "I am driving down to the Southern Valley casting plant," I told Marcus. Marcus looked at the map, then at the heavy steel vault where the 60-centimeter lens sat in the dark. "Thomas won't welcome an optical tech poking around his annealing ovens, Alan. Foundry men treat glass like liquid iron, they don't have patience for fractions of a wavelength." "I don't need his patience," I said, picking up my coat and my leather field notebook. "I only need to see the mold plates they use to pour the core." The Southern Valley Casting Foundry sat along the stony bank of the regional river, 3 miles south of the main industrial rail junction. It was an imposing complex of dark corrugated iron buildings, brick chimneys venting white steam into the gray autumn sky, and vast outdoor storage yards stacked with iron casting frames, wooden shipping crates, and tons of raw silica sand. The air in the valley smelled of burning coke, sulfur, and pulverized limestone. Unlike the immaculate, dust-free environment of our optical laboratory, the foundry was a place of heavy mechanical force, heat, and physical noise. Giant overhead cranes rumbled along steel gantry tracks, carrying 10-ton ladles of molten slag, while the constant, rhythmic thud of pneumatic drop hammers shook the gravel roads outside the main processing hall. I arrived at 11 o'clock, parking my small utility truck near the administration annex. I carried only my leather briefcase containing the high-resolution Foucault test photographs, my optical measuring calipers, and the official procurement paperwork for the meteorological refractor. I was met at the entrance by Thomas, the foundry's casting supervisor. Thomas was a broad-shouldered man in his late 50s, dressed in a heavy canvas work jacket with singed leather cuffs. His face was lined from decades of standing before open furnace ports, and his graying hair was cut short and functional. He carried a heavy clipboard crammed with furnace temperature charts and production quotas. "You're the optical technician from the Valley Lab," Thomas said, offering a firm, brief handshake. His voice had the gravelly rasp of someone who spent his days shouting over the roar of natural gas burners. "David called down from the municipal office. Said you were holding up a delivery over an internal wave in the glass." "I am holding the delivery because the glass contains structured internal density inclusions, Thomas," I replied, keeping my tone professional and grounded. "I need to inspect the casting logs and the annealing molds for Unit 4. Thomas let out a short, dry breath that was almost a laugh. "Alan, we melt 12 tons of borosilicate glass every 48 hours in this hall. We pour it into refractory clay molds, wheel it into the annealing layers, and let it cool according to strict time temperature curves approved by the State Standards Bureau. We don't handcraft individual bubbles into the melt. If there's a refractive wave in your blank, it came from a localized draft through the layer doors during the 45-day cooling cycle. A localized draft does not form legible numerical script, Thomas," I said quietly. Thomas stopped walking along the concrete gangway. He turned his head and looked at me with a sharp, piercing squint. "What did you say?" Instead of answering with words, I opened my briefcase, took out the high-contrast 8x10 monochromatic photograph I had captured through the Foucault viewing port, and handed it to him. Thomas looked down at the image. The photograph showed the dark, circular disc of the 60-centimeter lens, rendered in smooth optical gray, with the crisp, unmistakable sequence 8-4, 1-2 glowing in the upper left quadrant. Thomas's posture changed instantly. The casual, dismissive authority of a senior plant supervisor vanished, replaced by a rigid, concentrated stillness. He held the photograph with both hands, his callous thumbs resting on the clean white border, staring at the numbers for a long, unbroken moment. "How did you resolve this?" Thomas asked, his voice dropping below the ambient din of the plant floor. "A standard Foucault knife-edge apparatus with a monochromatic green point source," I replied. "Cutting the beam at the exact radius of curvature. The sequence is embedded 3 inches below the front surface. It was placed there during the ladle pour, before the blank entered the primary annealing layer." Thomas looked away from the photograph, his eyes scanning the cavernous furnace hall around us. At the far end of the bay, 3 massive cylindrical gas furnaces were roaring, their observation ports glowing with intense orange brilliance. Workers in reflective silver aprons were guiding an overhead crane toward the casting floor. "Walk with me," Thomas said quietly, handing the photograph back. "Keep your safety glasses on and stay on the yellow walkway." He led me past the roaring melt tanks to the rear of the complex, where the annealing layers were situated. The layers were massive, insulated brick tunnels 50 feet long, fitted with electric heating elements designed to lower the temperature of hot cast glass by less than 1 degree per hour over several weeks to relieve internal molecular tension. Unit 4 stood at the end of the line. It was an older, brick-encased layer with heavy iron doors secured by dual mechanical locking bars. Thomas stopped beside the control console of Unit 4. The temperature chart on the wall showed a continuous ink needle trace dating back 3 months, recording the steady, uninterrupted descent from 1200 degrees down to room temperature. "The molds for the meteorological blanks don't come from our standard pattern shop," Thomas said, leaning against the cold iron frame of the control box. "They are supplied directly by the Regional Infrastructure Department's Technical Division. Pre-assembled refractory steel casings, delivered sealed in wooden crates with specific instructions that they are not to be opened or altered prior to the pour." "Who delivers them?" I asked. "A private transport service contracted by Victor's office," Thomas explained, referring to the technical director whose signature appeared on the procurement requisition. "They bring the casting frame down to this bay 48 hours before a scheduled pour. We set the frame on the pouring table, hook up the preheating burners, and ladle the molten glass directly into the top gate." "And the core of the mold?" "The frame has an internal mandrel, a central steel plate suspended inside the mold cavity to regulate thermal dissipation during cooling," Thomas said, his voice measured and precise. "We were told the internal mandrel was designed to prevent center void cavitation in thick blanks. We don't inspect the internal geometry of the mandrel. Our job is simply to ensure the molten glass fills the void without trapping air pockets." "May I see the casting frame for the next scheduled pour?" I asked. Thomas shook his head slowly. "There isn't another pour scheduled for Unit 4. The meteorological refractor was the final blank on the contract. The transport crew came yesterday afternoon, loaded the used steel casting frame into an unmarked flatbed truck, and hauled it away." "Did you sign the bill of lading?" "Yes," Thomas said. He reached into the metal filing cabinet beside the console, flipped through a stack of yellow dispatch slips, and pulled out a single sheet. I leaned over his shoulder to examine the document. The dispatch slip was standard municipal stationery, recording the removal of refractory mold assembly M84. The destination line was not an address or a public department facility, it was listed simply as Sector 12, Maintenance Reserve Depot. Beside the destination was the signature of the driver who had accepted the equipment. The signature was a single, stylized initial, V. I looked at Thomas. "How long has Unit 4 been casting blanks using these specialized mandrels?" Thomas looked at the temperature chart on the wall, his gaze following the ink line back through the months. 18 months. 4 blanks total. The first was an optical flat for the regional survey tower. The second and third were the survey lenses you saw in your shop. The fourth was your 60-centimeter refractor. And every single blank was poured into a mold containing a suspended internal steel structure," I said, completing the equation in my mind. "If your photograph is accurate," Thomas said, his face shadowed by the flickering light of a distant burner, "then every piece of glass that came out of Unit 4 carried a set of numbers inside its core. The question isn't how they got there, Alan. The question is why a technical director in the infrastructure department is embedding optical grids into every surveying and weather instrument in the province. As Thomas spoke, the high-pitched whistle of the shift change sounded across the foundry floor. The roar of the overhead cranes slowed, and the heavy iron doors at the far end of the base swung open to admit the afternoon maintenance crew. Among the workers entering the hall was a tall man wearing a dark wool coat and carrying a leather dispatch case under his arm. He did not look like a foundry laborer. He moved with the brisk, controlled efficiency of an administrator. He stopped at the edge of the gangway, his eyes fixing directly on Thomas and me standing beside the Unit 4 control console. For 3 seconds, our eyes met across the smoky, half-lit expanse of the industrial hall. Then, without saying a word, the man turned on his heel, walked out through the side access gate, and disappeared into the autumn mist. When a technician discovers that an industrial anomaly is not an isolated defect but part of a systematic sequence, the entire geometry of the problem expands. The mystery was no longer confined to my testing tunnel or the casting floor of the foundry. It was anchored across the physical geography of the entire Northern Territory. I returned to our optical workshop late Wednesday afternoon. The valley was covered in a dense, low-hanging autumn fog that swallowed the sound of the river and turned the headlights of my truck into pale, milky cones. Marcus was waiting in the testing tunnel, sitting quietly on his iron stool. The green LED light source was still running, casting a faint emerald glow across the polished face of the 60-centimeter refractor lens. I walked in, closed the heavy soundproof door behind me, and laid the yellow foundry dispatch slip on the small equipment table. The molds were supplied prefabricated by the infrastructure office, I told Marcus, unbuttoning my coat. An internal steel mandrel was suspended inside the mold cavity during the ladle pour. 4 blanks were cast over 18 months. All 4 were delivered to this workshop. All 4 were crowned, polished, and certified by us. Marcus looked at the dispatch slip, then up at the lens resting in its padded wooden cradle. 4 blanks. The survey flat, the 2 survey refractors, and this weather lens. Look at the sequence of the numbers we have verified, I said, pulling out my notebook and writing the figures down on a clean sheet. Instrument 1, survey flat 8. Instrument 2, survey refractor A 8 to 4. Instrument 3, survey refractor B 8 to 4 1. Instrument 4, meteorological lens 8 to 4 1 to 2. Marcus leaned forward, his wire-rimmed glasses reflecting the green test light. It's an accumulation. Each instrument carries the previous digits, plus 1 additional number. It is not a serial number, I explained, sitting on the edge of the work trolley. It is a set of spatial coordinates based on a 4-tiered hierarchical grid system. In geodetic surveying, an 8-digit or 4-parameter code is used to designate specific quadrants of land. The first digit defines the major regional sector. The second defines the subsector. The third defines the local land parcel, and the fourth defines the precise structural point. Sector 8, Marcus murmured, looking toward the regional map on the wall. The entire northern agricultural basin is designated as Sector 8 in the Municipal Property Registry. Subsector 4 is the Western River Valley, I continued, tracing the lines in my memory. Parcel 1 is the industrial corridor along the railway line. And point 2. I stopped. Marcus looked at me. What is point 2? Point 2 is the underground municipal reservoir and water treatment facility at the base of the Western Ridge, I said quietly. The primary freshwater distribution hub for the entire northern province. Marcus stood up slowly, his hands resting on his hips as he turned to face the 60-centimeter lens. Alan, why would someone embed optical coordinates pointing to the regional water reservoir inside a high-altitude meteorological refractor? Because the meteorological station doesn't just watch the weather, I said, the technical reality clicking into place with cold, mathematical precision. The weather station sits on the mountain summit at an elevation of 6,000 feet. From that height, an automated optical instrument pointed down into the valley with a 60-centimeter aperture can resolve physical details down to several inches across a 30-mile radius. A visual surveillance alignment, Marcus whispered. Not visual surveillance for human eyes, I corrected. An optical sensor array. If you mount an automated digital photometer or an infrared scanner behind this lens, the embedded internal numbers 8 to 4 1 to 2 act as a permanent, hard-coded fiducial marker on the focal plane. Every image recorded by the sensor is automatically stamped with the exact physical alignment grid of the reservoir facility, completely independent of the telescope's external software or electronic telemetry. Software can be hacked, wiped, or recalibrated, Marcus realized, his eyes widening. An optical watermark inside the glass itself is permanent. It cannot be altered by a computer glitch or a network failure. The lens physically forces the sensor to align with that exact geographic point. And whoever manufactured the mold, I added, remembering the stylized signature on the dispatch slip, ensured that the entire regional survey network was aligned to the same baseline. I walked over to the desk, pulled out the technical procurement manual for the meteorological station, and turned to the structural specifications for the mountain installation. The mountain facility was officially described as a regional atmospheric research station, funded jointly by the Municipal Infrastructure Board and the Regional Agricultural Council. Its stated purpose was to provide 3-day advance warnings for frost, hail, and high-altitude thermal inversions that could damage the valley's fruit orchards. However, as I read through the mechanical installation section, I noticed an anomaly in the mounting hardware specifications. The telescope barrel was not designed to point upward toward the sky at a standard astronomical zenith angle. The heavy steel mounting fork was engineered with a 45-degree downward tilt limit, designed specifically to lock the optical axis of the refractor between 15 and 30 degrees below the horizon, aimed directly down into the valley floor. I pointed the diagram out to Marcus. Marcus looked at the mechanical drawing, tracing the steel pivot stops with his thumb. It's a terrestrial observation telescope. It was never intended to look at the stars or the upper atmosphere. It was built to look down at the valley. And David from the municipal office told me the transport team is arriving tomorrow morning at 9 to take it up the mountain, I said. What are you going to do, Alan? Marcus asked. If you refuse to sign the certificate, they will simply seize the instrument under the Emergency Public Works Act. David has the legal authority to take possession of municipal property if a contractor creates an unauthorized delay. I am not going to refuse to sign the certificate, I said, picking up my drafting pen. I am going to complete the optical certification exactly according to professional standards. But I am going to document the refractive inclusion on the official public record. I pulled a blank certificate of optical verification from the drawer, the formal, 3-page document printed on heavy parchment paper with the regional guild's embossed seal in the corner. I wrote down the physical measurements with meticulous precision. Clear aperture, 600.00 millimeters. Focal length, 2400.00 millimeters. Surface accuracy, 0.05 waves, sodium D-line. Internal homogeneity, non-standard. Structured refractive inclusion detected at coordinate X, plus 142.5 millimeters, Y, plus 210.0 millimeters, sequence verified as 8 to 4, 1 to 2. I signed the bottom of the parchment in permanent black iron gall ink, applied the embossed metal seal over my signature, and affixed one copy to the wooden transport crate. The second copy went into my private field briefcase. The third copy was filed in our permanent workshop vault. At 8 o'clock that evening, as I was locking the heavy iron shutters on the workshop windows, my personal telephone in the cottage down the valley rang. I picked up the receiver. Alan, said a calm, low voice. It was not David, and it was not Thomas. It was the measured, deliberate voice of someone accustomed to speaking with quiet authority. Who is this? I asked. My name is Victor, the voice replied. I am the technical director for the Regional Infrastructure Board. I held the receiver firmly against my ear. Outside, the valley wind was picking up, rattling the dry branches of the apple trees against my window pane. You're the man who designed the internal mandrels for the unit forecasting molds. I am, Victor said without hesitation. And I understand you spent your afternoon at the foundry with Thomas, asking questions about manufacturing processes that lie outside your contract. My contract requires me to certify the optical quality of precision glass, Victor, I replied evenly. When a 60-centimeter refractor contains a hard-coded geographic alignment grid inside the melt, it is my professional duty to document the inclusion. There was a brief pause on the line. Alan, Victor said softly, his voice remarkably steady. You are an exceptional optical technician. You understand light, glass, and surfaces better than anyone in this province. But you are looking at a single component of a system whose scale you have not yet measured. Then explain the system, Victor, I said. Meet me tomorrow morning at 7 o'clock, Victor replied. Before the transport crew arrives at your workshop. Come to the old water pumping station at the base of the western ridge, point 2 on your grid. I will show you why the glass was poured with those numbers. The line went dead with a clean, mechanical click. The old water pumping station sat in a narrow granite ravine at the base of the western mountain ridge, 2 miles west of the main agricultural canal. It was an austere, red brick structure built 80 years ago during the original electrification of the valley, partially embedded into the living rock of the cliffside. A heavy steel pipeline, 6 feet in diameter, emerged from the mountain face behind the building, plunging into the ground to feed the subterranean distribution network that supplied 60,000 acres of farmland and 3 municipal townships. I arrived at 10 minutes to 7 on Thursday morning. The valley below was still cloaked in pre-dawn shadows, but the high granite peaks above were beginning to catch the pale, cold amber of first light. The air was crisp, hovering near freezing, smelling of wet stone, pine needles, and the deep, metallic chill of fast-moving water. I parked my truck on the gravel turnaround beside the massive iron intake gates. I had brought my briefcase containing the optical certificates, my high-powered LED inspection torch, and a handheld optical collimator. A single dark green municipal utility vehicle was already parked beside the pump house doors. Standing near the concrete intake channel, leaning against the iron railing with a steaming thermos cup in his hand, was Victor. Up close, Victor looked less like a shadowy bureaucrat and more like a senior civil engineer who had spent decades managing large-scale public works. He was in his early 60s, with silver hair cropped close, wearing a weathered wax canvas field coat and heavy leather work boots. His face was lined with the quiet, focused gravity of someone who carried the weight of complex physical systems in his head. He turned as my boots crunched on the gravel. "You're punctual, Alan," Victor said, his voice calm and unhurried in the cold air. "Optical instrument makers usually are. You can't rush class, and you can't rush time." "I am here for an explanation, Victor," I said, stopping 6 feet from the railing. "Not a philosophy lesson." Victor smiled faintly, took a sip from his thermos, and nodded toward the heavy iron door of the pump house. "Come inside. The explanation is 50 feet below this floor." He pulled a heavy brass mortise key from his pocket, unlocked a reinforced service door, and pushed it open. The interior of the building was a vast, echoing hall dominated by 2 massive electric turbine pumps painted industrial green. The floor was spotless gray concrete, vibrating faintly with the low, continuous 60-cycle hum of high-voltage transformers. A steel spiral staircase descended into a central vertical shaft between the 2 turbines. Victor led the way down the spiral stairs. As we descended, the air grew noticeably colder and damper. The concrete walls of the upper building gave way to rough-hewn granite masonry reinforced with heavy steel rock bolts. We reached the bottom landing 50 feet below ground level. Before us stretched a long, vaulted tunnel illuminated by caged bulkhead lights. Running along the center of the floor was a massive, horizontal hydraulic manifold, a complex junction of steel pipes, motorized gate valves, and high-pressure pressure relief bypasses. Victor walked to the center of the manifold, stopping beside a large, circular observation chamber fitted with a 12-inch thick optical quartz viewing port. "Do you know what this facility actually does, Alan?" Victor asked, shining his torch into the viewing port. "It regulates the hydrostatic pressure from the high-altitude mountain reservoir before the water enters the valley distribution mains," I answered, looking through the thick quartz window. Inside, a massive stream of dark, high-velocity water was churning through a constriction nozzle with immense force. "That was its original purpose 80 years ago," Victor said. "Today, it does something far more critical. The mountain above us is an unstable geological formation, a layered sandstone and shale cap resting on a fractured limestone base. Over the past 12 years, tectonic settling along the western fault line has created microfractures in the deep subterranean drainage channels beneath the reservoir." I looked at him, my mind immediately processing the engineering implications. "The reservoir is leaking into the mountain foundation." "Not leaking in a catastrophic sense," Victor corrected carefully. It is migrating through microscopic fissure networks. When the water table rises after heavy autumn rains, the hydrostatic pressure inside those rock fractures increases. If the pressure exceeds 32 bars, the entire eastern slope of the ridge, roughly 40 million tons of rock and soil, will suffer a progressive shear failure. A landslide, I said. A landslide that would obliterate this pumping station, sever the primary railway line, and flood the entire southern industrial basin within 45 minutes, Victor stated with absolute, flat certainty. We cannot stop the geological migration. We can only manage it by dynamically adjusting the release valves along this manifold to relieve pressure in the deep rock strata before the shear threshold is reached. And how do you measure the pressure in the rock strata? I asked, looking from the manifold to his face. Victor reached into his coat pocket and pulled out a small, precision optical flat, a 4-inch disc of polished glass identical in material and finish to the survey flats we had ground in our workshop 2 years earlier. Piezometric pressure gauges mounted inside deep boreholes across the mountain, Victor said, holding the glass disc up to the bulkhead light. Each borehole is fitted with an optical interference transducer, a glass prism whose refractive index shifts in direct proportion to the mechanical strain exerted by the surrounding rock. He turned the glass disc slightly. In the center of the disc, visible under the angle of the overhead lamp, was the tiny, embedded number 8. Sector 8, I whispered. The borehole network spans 4 tiers, Victor explained, his voice resonant in the damp subterranean tumult. Tier 8 covers the regional baseline. Tier 84 covers the western slope. Tier 841 covers the primary fault fracture. And Tier 812.2 is the deep hydraulic anchor directly beneath the mountain meteorological station. The mountain weather station isn't a weather station, I realized, the entire multi-year sequence aligning into a single, cohesive structure. It is an automated optical telemetry hub. It is the central monitoring observatory for the entire mountain stabilization system, Victor said. The 60-centimeter refractor you polished is the primary optical receiver. It sits in the summit dome, pointed directly down at this ravine. It collects the laser telemetry beams transmitted by the optical transducers in each borehole. And the numbers embedded inside the glass? I asked. Victor looked at me with deep, professional respect. In an optical telemetry system operating across 30 miles of turbulent atmospheric air, thermal scintillation and wind shear cause the incoming light beams to dance and wander across the sensor plane. If the receiver uses standard software calibration, an electronic glitch or a sudden atmospheric distortion could miscalculate the strain reading by a fraction of a percent, leading the automated system to open the wrong release valve and trigger the very collapse we are trying to prevent. He paused, resting his hand on the steel manifold pipe. By embedding the geometric numbers 8 to 4, 1 to 2 directly into the molecular core of the objective lens, Victor continued, we created an immutable, physical optical datum. The incoming laser signals from the boreholes pass through the exact same glass matrix as the fiducial numbers. No matter how much the air shimmers, no matter how severely the software glitches, the physical refraction of the glass forces the sensor to calculate the strain against a permanent, unchangeable baseline. The explanation was complete. It was grounded entirely in advanced optical physics, civil engineering, and public safety. There was no conspiracy, no unauthorized surveillance, and no criminal deceit. It was an extraordinary, brilliant piece of physical fail-safe engineering designed by a master technician who understood that when human lives depend on a measurement, you do not trust software, you trust the unyielding laws of glass and light. Why the secrecy, Victor? I asked, looking around the subterranean tunnel. Why hide the mandrels in the casting foundry? Why force the procurement through an ordinary weather station requisition? Victor sighed, his breath forming a pale plume in the cold air. Because 10 years ago, when the first geological report was presented to the municipal council, the politicians panicked. They wanted to condemn 60,000 acres of prime agricultural land, relocate 2 townships, and shut down the valley's economy out of fear. When cooler heads prevailed, they slashed the stabilization budget by 60% and ordered us to study the problem. He looked me in the eye. I didn't have time to study a mountain that was moving 4 millimeters a year, Alan, Victor said quietly. I had to build the monitoring network under existing maintenance and meteorological allocations. I couldn't explain to a municipal procurement clerk why an atmospheric weather station needed an optical blank with specialized refractive mandrels. So I designed the molds myself, delivered them to Thomas, and sent the blanks to the finest optical technician in the province. I stood in the quiet tunnel for a long moment, listening to the deep, powerful hum of the water moving through the rock beneath our feet. The equation was balanced. Every anomaly had found its physical mechanism. Every mark in the glass had fulfilled its purpose to the exact fraction of a millimeter. The transport crew was arriving at the workshop at 9, I said. Victor nodded. I know. The installation team is waiting on the summit. I opened my briefcase, took out the 3-page certificate of optical verification, and laid it flat on the metal top of the valve housing. I took out my pen, crossed out the word non-standard under the internal homogeneity line, and wrote in clean, firm letters. Verified structural optical datum alignment confirmed to specification. I handed the certificate to Victor. Let's get the lens up the mountain, I said. The ascent to the summit observatory was a 3-hour journey along a narrow, winding service road cut into the sheer granite face of the western ridge. The autumn mist that had blanketed the valley floor gave way at 4,000 feet to brilliant, cold alpine sunlight and an endless expanse of deep blue sky. I rode in the passenger seat of the heavy municipal transport truck, my eyes fixed on the rearview mirror where the padded wooden suspension crate carrying the 60-centimeter refractor was strapped securely to the reinforced chassis. Victor drove with the steady, calm precision of someone who had traversed these mountain switchbacks hundreds of times. Behind us, a second utility truck carried Marcus, who had insisted on accompanying the installation team. No one bolts a 60-centimeter doublet into a steel cell without my torque wrench, Marcus had declared before we left the workshop. Foundry engineers think 30 foot-pounds is gentle, they'll warp the crown element before the sun goes down. We reached the summit plateau at 12:30. The installation was perched on the highest rocky outcrop of the ridge, a circular, white domed tower constructed of reinforced concrete anchored directly into the basalt bedrock. Unlike an astronomical observatory, which features a vertical slit in the dome that opens upward toward the stars, this facility featured a wide, continuous horizontal bay window of optical-grade glass angled 15 degrees downward, looking out over the immense panoramic expanse of the valley 60 miles below. The interior of the dome was a clean, brightly lit technical workspace filled with electronics racks, high-speed multi-channel data recorders, and high-pressure nitrogen purging lines. In the center of the floor stood the massive equatorial mounting pier, a 4-ton cast-iron pedestal supporting a heavy steel optical barrel 10 feet in length. The on-site engineering crew was managed by an electronics technician named Sarah. Sarah was in her late 30s, wearing a fleece vest covered in tool clips, with a digital diagnostic tablet strapped to her forearm. Victor, Sarah called out as we entered the dome. The borehole laser array in Sector 8 is active. All 4 telemetry beacons are transmitting on the 532-nanometer green line. We've been waiting for the objective to establish the master optical zero. The objective is here, Sarah, Victor said, introducing Marcus and me. Alan verified the optical datum this morning. Marcus is here to supervise the mechanical mounting. For the next 4 hours, the dome became a hive of disciplined, quiet precision. Marcus took charge of the mechanical assembly. Using a lightweight overhead gantry crane, we lifted the 60-centimeter glass lens from its velvet-lined shipping cradle. Under the crisp mountain sunlight streaming through the dome windows, the glass blank appeared completely transparent, perfectly polished, without the slightest visible trace of the internal numbers that had started our journey. Marcus guided the heavy brass retaining cell around the perimeter of the glass, tightening the 12 radial centering screws with his calibrated torque wrench, checking the gap at every quadrant with brass feeler gauges to ensure zero mechanical pinching. By 4 o'clock, the lens assembly was bolted securely to the front flange of the 10-foot steel barrel. Optical cell secured, Marcus reported, wiping his brow with a blue shop rag. No strain on the glass. The figure is true. I stepped up to the rear instrument station of the telescope. Instead of an eyepiece for human observation, the focal plane was equipped with a high-resolution, thermoelectrically cooled CCD camera array connected to an optical interferometric analyzer. Sarah, I said, sitting at the control console. Power up the receiver array and open the dome shutter. The heavy electric motors hummed to life. The motorized steel shutters rolled back with a low, smooth rumble, exposing the 60-centimeter lens to the vast, sunlit panorama of the valley below. Through the angled bay window, the entire territory lay mapped out like an immense living blueprint. The silver ribbon of the regional river wound through the green patchwork of agricultural fields in Sector 8, the brick chimneys of the casting foundry in the southern valley were venting tiny plumes of white smoke, and at the base of the granite cliff directly below us, the red brick water pumping station stood beside its frothing intake channel. "Engaging laser telemetry beacons," Sarah said, tapping her tablet. 30 miles away, across the valley floor, four tiny, invisible green laser transmitters emitted continuous, synchronized pulses of light toward the mountain summit. On my console monitor, the raw video feed from the telescope's focal plane flickered to life. At first, the display showed only a blur of turbulent, shimmering light as the incoming laser beams struggled against the rising thermal currents of the valley air. The digital software crosshairs on the screen jumped and drifted erratically, unable to lock onto a stable tracking coordinate. "Atmospheric scintillation is running high," Sarah noted, watching the data curve fluctuate. "Thermal drift is plus or minus 12 arcseconds." "Engage the optical knife-edge filter at the primary focus," I instructed. Sarah threw a mechanical switch on the instrument panel. Inside the rear barrel of the telescope, a precision razor-edge filter slid into the light path at the exact focal plane of the lens, replicating the Foucault test geometry under real-world operating conditions. The monitor screen darkened instantly, the turbulent white glare fading into that familiar, velvety optical gray. And then, with breathtaking, crystalline clarity, the internal structure of the lens manifested on the screen. Floating serenely above the shimmering green laser points, completely motionless against the shifting atmospheric currents, was the crisp, glowing sequence. 8 to 4, 1 to 2. The four green laser beacons from the valley below did not drift randomly across the screen anymore. The optical refractive shift built into the glass matrix acted as an invisible physical funnel, locking each laser point into its precise geometric quadrant around the embedded digits. The numbers 8 to 4, 1 to 2 sat directly over the laser returned from the subterranean pumping station at the base of the cliff. On the diagnostic terminal, the erratic data curve stabilized into a flat, razor-sharp line. The strain readout from the deep borehole beneath the reservoir resolved with absolute precision. Borehole 8412, hydrostatic pressure 24.6 bars, stable. Sarah stared at the glowing numbers on the display, a slow, radiant smile breaking across her face. "The optical datum is holding. Thermal scintillation drift is reduced to 0. The telemetry lock is absolute." Victor stood behind my chair, his hands resting on the back of the console, looking at the display in complete, reverent silence. The long, complex journey that had begun with a stray shadow in a dark testing tunnel had reached its final, triumphant destination. The mountain was watched. The valley was safe. The glass had fulfilled its silent, extraordinary destiny. I leaned back in the chair, looking through the high dome window at the setting sun casting long, golden shadows across the vast landscape below. "Everything fits together now," I said quietly. 2 weeks after the installation on the summit, the autumn weather in the valley finally broke. The persistent low fog that had clung to the river banks was swept away by a clean, crisp northwesterly wind, bringing bright, cold mornings and crystal-clear skies. The apple harvest in the Orchard Valley reached its peak, with lines of wooden farm wagons rolling along the rural roads, their crates piled high with red fruit, completely oblivious to the silent sentinel watching over them from the granite peak above. Our optical workshop returned to its familiar, rhythmic routine. Marcus was back at his drafting table, wearing his half-moon reading glasses, meticulously inking the mechanical specifications for a set of 30-centimeter parabolic mirrors destined for a regional university observatory. The air in the rough shaping room was filled once more with the steady, wet hiss of the grinding wheels and the faint, clean scent of cedar sawdust and mineral oil. I stood at my workbench in the fine polishing bay, holding a 4-inch concave test plate under the monochromatic sodium vapor lamp. The yellow light cast clean, concentric Newton rings across the glass, showing a surface true to within 1/50th of a wavelength. At 10 o'clock, the workshop door opened, and David, the logistics coordinator from the Municipal Infrastructure Department, stepped inside. He was carrying a thick leather folder under his arm, but his usual hurried, bureaucratic irritation was entirely gone. He walked across the concrete floor with a measured, respectful pace, stopping beside my assembly table. "Alan," David said, nodding politely. "I have the final closeout documentation for the meteorological refractor project." He laid the paperwork on the zinc counter. It was a formal municipal resolution, signed by the chairman of the Regional Oversight Board and countersigned by Victor. The document formally accepted the 60-centimeter refractor into the Permanent Public Asset Registry, accompanied by a special commendation for our workshop's exceptional adherence to precision material verification. Attached to the resolution was an official revision to the regional procurement guidelines. From this day forward, all specialized optical blanks produced by the Southern Valley Foundry were recognized under a new public classification, Precision Geodetic Datum Substrates. There would be no more secret mandrels, no more disguised requisition forms, and no more administrative evasion. The monitoring system was now a recognized, legally protected public infrastructure project with a dedicated annual maintenance budget. "Victor asked me to deliver this personally," David said, handing me a small, velvet-lined wooden case. "He said you should have it for your workshop archives." I took the wooden case, unlatched the brass hook, and opened the lid. Inside, resting on a bed of dark blue silk, was a 2-inch circular disc of polished optical crown glass, the test sample cut from the edge of the 60-centimeter meteorological blank before it entered the annealing layer. I carried the disc into the testing tunnel, placed it under the Foucault inspection light, and slid the knife edge across the beam. In the center of the small glass circle, rendered in crisp, perfect light and shadow, was a single, elegant letter. Phi. I smiled, turned off the light, and returned to the main workshop. "Did Victor mention how the mountain is behaving?" I asked David. "We had 2 inches of heavy rain across the ridge on Tuesday night," David replied, leaning against the counter. "The hydrostatic pressure in the lower strata rose by 3 bars. The summit telemetry system detected the microstrain instantly, and the automated bypass valves at the pump house opened for 20 minutes to vent the excess water into the river canal. The pressure dropped back to normal within an hour." He looked at me, shaking his head slightly with genuine professional wonder. "The valley never even felt a tremor." "That is the purpose of a good instrument, David," I said, closing the velvet case. "When it does its job properly, nobody notices it was ever there." David smiled, shook my hand warmly, and departed through the main gate into the autumn sunshine. After lunch, Marcus and I walked out to the small grassy terrace behind the workshop. We stood beside the stone wall, looking up at the majestic wall of the western mountain ridge rising 40 miles away. High on the granite summit, catching the bright afternoon sun like a tiny spark of silver light, sat the white dome of the observatory. Through 60 miles of open air, the 60-centimeter glass lens was sitting in its heavy steel barrel, perfectly still, perfectly clear, holding the entire province inside its silent, unyielding geometric gaze. I thought about the molten sand in Thomas's roaring furnaces, the slow, 45-day descent of the cooling layers, the thousands of circular polishing strokes with diamond grit, and the 4 numbers buried deep inside the molecular heart of the glass. Reality had not stuttered. The equation had never broken. Human hands had simply reached into the fire, shaped the light, and laid a permanent truth inside the stone and glass of the world. I turned back toward the workshop door, pulled on my shop apron, and picked up my polishing lap. There was another blank waiting on the spindle, and the glass was ready to be ground.